Okay, and first, just a disclaimer that we put at the start of every one of our robotics and planning tutorials so far, which is that whenever we say planning, one of 4 or 5 different things can be heard by the other person. When I say planning, I mean task planning. So I mean PDDL planning or RDDL planning, as opposed to grasp planning, path planning, motion planning, all of which will be involved in robotics and is very important for task planning in robotics. But I'm just going to be saying planning, and I mean task planning when I do. So before I get into the main tutorial, just a bit about what we do in King's College. We're part of the Human AI Teaming Lab there. And for a while now, we've been focusing on trying to apply task planning in real situations. So first of all, in robotics, in autonomous underwater vehicles, in probabilistic planning with service robots, we're really interested in seeing our planners actually working on some physical hardware. But also outside of robotics, with humans, right now, I think 3 of our members are giving talks in the explainable planning workshop upstairs. And in non-robotic, slightly less human domains, such as the smart buildings, combined room booking and heating, ventilation, air conditioning system planning and things like this. But we're not so interested in just writing planners, solving plans and moving on to the next heuristic. We really want to see our plans doing things, and that's what got us into robotics in the first place. So I'll just explain our sort of robotics and planning journey in order to frame what ROSPlan is and what it is to task planning in robotics. So my first engagement with robotics was in the Pandora project with these autonomous underwater vehicles for planning, inspection and maintenance tasks of seabed facilities. So we had this is the Girona 500. There was also the Nessie AUV from Heriot Watt. And the idea was that these AUVs were meant to go down to the seabed, to these manifolds, where there were many pipes and joints and welds, where they would inspect these things for wear and tear, but also perform some maintenance, such as valve turning and cleaning chains with high pressure hoses. What made this interesting to us was that we wanted to send these AUVs down there for days or weeks at a time without any human intervention. And we quickly realized that these problems were far too large for our planners to solve. So we had to start thinking about architectures that were able to compose multiple different planning problems together. And then the second thing we ran into was that as soon as the mission began to execute, the real world would deviate from what was expected in the planning model. And it would do so in all sorts of ways that we hadn't really thought about at the time. So I like to think that as soon as you begin to execute the plan, you begin to patch holes. You start hacking around in the system architecture until you have something that's able to complete the mission, but maybe it's not as general as you'd like. Our part in this project was really just integrating the planner to control these AUVs, and that turned out to be a tremendous amount of work just in integration, and then patching all of these things. And at the end we had a nice system, but it was good for this mission. After Pandora we moved on to Squirrel, where again we were in charge of linking a planner to the robot so that this robot was able to plan its activities. In this case, the activities were to enter a room, to play with children, to tidy toys, and to clean up clutter. And there we ran into all sorts of problems which we hadn't had in Pandora. In Pandora, we have a blueprint of the seabed manifold. Nothing gets built down there unless it's already really well designed and well known, where everything's going to be. Whereas in a children's room, it's not like that. Before the robot enters the room, it doesn't even know what objects might be in there. And at this point, how do we even construct an initial state from which to plan if we don't have this list of objects that are going to be in the room? So again, we started to come up with solutions about how to compose different plans together, exploration plans to build lists of objects, and then plans to tidy them up afterwards. And again, the system that we built had a lot of add-on pieces to deal with problems that we hadn't foreseen, and it turned out to be a lot of implementation work. But we did notice that a lot of the implementation we did was the same as what we'd had to do in Pandora. There were these elements which were common to both. And that's what ROSPlan was born from. We extracted those common elements and we tried to make them as tidy as possible so that if we were given a chance at a third robotics project, we wouldn't have to do it again. And since then we've played with a lot of different robots, and found ROSPlan is quite fun to use, at least. Okay, so task planning and robotics. At the end of this tutorial, I will have a list of all of the references. The first one on the list is this survey paper from Ingrand and Galab, which is, I think, extremely good and well worth the read. But in that paper, the authors identify these different deliberation functions that a task planning robotic system performs. The one I'm interested in most, of course, is planning, which I would identify as the deliberation function of organizing actions to achieve goals before starting to execute them. And in a bit more detail, although there are many variants of planning, what I'm used to is a domain model and a problem instance. So a domain model that describes the capabilities of the robot and the environment and its internal state, and a problem instance which just describes the initial state and the goal condition. These are passed to a planner, which then produces a plan. So an important aspect of this is that your domain model is a model of the world that can be used to predict the outcomes of actions and anticipate the behavior and change in the environment around the robot. Having such a model is already quite a big assumption. In some of our other work, for example, heating, ventilation, air conditioning, the energy grid stuff, having a model wasn't quite as strong an assumption. There were physical effects. We could use physics to model it, and it was fairly predictable what was going to happen. In robotics, that's not the case. If you try to execute the same action on the robot 5 times, you may end up with 5 different results. And then when you try the 6th time, the battery just might be too low, and it does half the action. So most of what I'll talk about today is how do we deal with the fact that we want to have a model that's possible to plan with, but at the same time accurate enough for the real world. But assuming we have that, then it should be easy for the robot to follow a plan. We have some really nice libraries, which I'll go into in a moment. ROS, and the robot can have a set of interfaces which are a list of actions that the robot can perform, buttons you can push, go here, pick up this. Given that, if you model those actions in your PDDL domain, you should be fine, except, as I just mentioned, the model is probably not going to be correct. Also, the model's probably not going to be accurate enough. This is always going to be the case that when I tell the robot to go over there, I'm not going to model exactly the path planning routine that is going to be executed when I perform this action. Otherwise, why do I even need the path planner? Second is the state can become mismatched with reality, and this is not the same as the model being wrong. It could be that the model is correct, but the robot just doesn't have the sensors which are able to populate that model with the current state. You could have a perfect model and a perfect initial state, but unless you have the sensors to keep that state up to date, as soon as things begin to change and the robot begins to move, then you are either relying on dead reckoning or luck. And there are many different reasons why these states can start to diverge and why the model can be incorrect. So this is just sort of a short list I made during the Plan Rob workshop yesterday about what are some of the challenges that are being addressed in task planning and robotics right now. So, I mean, even the first one is basically an open problem. As people say, you plan and then you execute the plan, but that's not actually the truth. The truth is, the mission begins, there's the robot, it's planning and the clock is already ticking. So how can you take into account the time it takes to plan while you are planning? And this is extremely important to consider the underwater environment of the Pandora project. There are strong currents there. If you begin to plan exactly how you're going to manipulate this valve panel while the current's pushing you away to the side, then you're either losing energy holding your position, or by the time you've figured out which valve panel to turn, the valve panel's, 4 meters away. What else is interesting here? This was a problem we encountered a lot in Squill. How do you plan when you only have partial information? What do we do before we open the door and go into the room? Is the best plan that we can really come up with open the door, then tidy the room as one action, or can we be more specific than that? Reaction to unexpected events, handling risk, all of these things come under plan execution. Plan execution has its own workshop here, but yeah, please.
Are you able to elaborate what's the reaction to unexpected events?
Yeah, sure. So, I mean, in its simplest form, it's that the robot has a model which is not only a model of what the world is like now, but it's a predictive model. It says, how will the world evolve? An unexpected event is a sensor reading or an observation which doesn't match this prediction. So, for example, the robot is trying to go home. It goes to the door, it expects the door to be open, and the plan is to move through, but the door is actually closed. This was unexpected, and in this case it invalidates the plan. And the question is here, if you come across an unexpected event, does it invalidate the plan? Does it invalidate the plan straight away, or can you fix it? So as an example, in the Pandora project, we would build a probabilistic roadmap around these large structures. In simulation, we would cause collapses where certain paths between the seabed structures would become obstructed. While the AUV was performing a maintenance mission, inspection mission, it would notice this obstruction. And sometimes that obstruction wouldn't invalidate the plan now, but invalidate the plan in 2 hours, because in 2 hours' time we're going to pass through this point. Do we have to stop and replan now, or can we continue executing the current plan and replan while we're executing? Well, that depends on whether the actions we're executing now are still useful, given that we're going to change the later ones. So what is an unexpected event is when the real world differs from what it was predicted to be, and how you react to that is actually a difficult decision that depends upon a lot of factors. It depends, what are we going to do next, and how does this unexpected event impact our plan? Another kind of unexpected event is an opportunity. So going back to the Pandora project again, because it's full of good examples, one of the missions we looked at was chain following. So chain following is sometimes the AUV is sailing through its mission and it sees a chain on the ground. This can often happen due to storms pulling the anchor chains loose from big ships. And if that happens, sometimes people don't notice that's happened. These big ships have a lot of different anchor chains. And it has happened before that remote operated vehicles have spotted chains lying on the seabed and gone, well, what are these? Followed it to one end and found that it's just not connected to anything. And they've discovered that one of these big ships has just snapped its chain in a storm. So if you find a chain, you should probably follow it to make sure it's not meant to be doing something important. But that's not a goal that was given to the AUV by a human. it's already performing a mission. This is an unexpected event as well. And in this case, your reaction to it could be, I could ignore it. It doesn't invalidate my plan. But the question is, should you ignore it? And here it depends on whether it's possible to replan to gain some extra utility by taking advantage of this unexpected event. So I'm going to plug in my laptop while presenting. Okay. Does anyone else have any questions about these? I'd love to hear more thoughts or just discuss them.
I'm interested in recovering from the state.
Recovering the state.
Recovering from the state of failure. Because if you have impartial information about the state,
Yep.
how do you recover?
I mean, sometimes you can't. This is actually, I think, probably the first problem I encountered in planning for robotics. I wrote a lovely domain for my robot. I had waypoints. I said, go to waypoint. The navigation action failed halfway through, and I said, replan, and it said the problem's unsolvable. Why was the problem unsolvable? Well, my go-to waypoint, the start effect is the robot's not at this location anymore. The end effect is the robot's going to be at the next location. But we didn't reach the end of the action. The action failed. So in the current state, the robot is nowhere. How do you recover from that? Our PDDL state is an abstraction of the real world, which only models parts of it. And right now we're between PDDL states. And how you recover that will depend on exactly what kind of state space you're looking at. Is it possible, so for this waypoint example, for example, you could just say, we're always going to assume that the robot is exactly at one of these waypoints, just whichever one it's closest to. But now your model's inaccurate in a different way. You could also have a recovery action where after the robot has moved towards a waypoint, you have a new fact, which is the robot was going to this waypoint, and a recovery action that is, please continue where you were going. But again, you don't know exactly what the state of the robot is in this case. You don't know where it is, how close it was when the action failed.
Or maybe why it failed.
Or why it failed. So there's an invited talk from Derek Long, possibly tomorrow, where he's going to talk about oil well drilling. And I think he's going to talk, hopefully he's going to talk about this a little bit, because what they're doing right now. Is it on Monday?
According to schedules.
I recommend it, because they're planning operations for, basically for a robot that is miles down in the ground. You can't really see physically what it's doing. You only have the sensor readings that it's sending back up. So when something does fail and it needs to replan, the state that it's in could be somewhere between, the drill is gripping and it's digging correctly, but something else has gone wrong. It's come off the bottom and it's spinning wildly, or it's somewhere in between where it's sticking and spinning. What you really need is some sort of conformant operation where you can say, all right, I'm going to send some signals to the robot that will move it from whatever strange state it's in to exactly one of my modeled PDDL nice planning states. But whether that kind of command is possible depends again on the state space you're looking at. Okay. So all of this combined, I'm interested in planning and making robots do plans, but the truth is, if you want to perform planning on a robot, you have to also perform at least these 3 deliberation functions. I think. So of course, if you want to plan on a robot, you probably have to look at how do you act on a robot? How do you take an action from the planner, decide when to execute it, and then convert that action from the state space of our planner, from our planner's model, into a goal that can be posted to one of the robot's actions. Observing is the way in which the state is updated, and we try and keep it as close as possible to the real world. And it's not just a bottom-up process of taking data from sensors and updating a state, but it's also a top-down process of where do we point those sensors? When do we take active sensing actions? How do we direct our observations in order to keep the state up to date? And then monitoring goes back to the problems I was talking about. How do you react to these unexpected events? Has the plan failed? And how do you need to respond to what the current state is, given your current plan? And all of these areas, these deliberation functions, involve many of the problems from the previous slide. So, as a result, this is a table taken from that survey paper of different system architectures for planning robotics. It's actually only half of the table. And I mentioned in the Plan World workshop yesterday, there are many different system architectures, each one geared to tackle some of the problems from that slide, but not all of them. And they all do something different. The system architecture we had in Pandora is different from the system architecture we built for Squirrel, which is different from the system architecture we're building for this multi-robot project that we're looking at now, because we're interested in solving different problems. And I don't think this is a bad thing. We have many different system architectures now. If you Google robot system architecture or something like that, you'll find just hundreds of pictures of boxes connected by arrows telling you, here's how the flow of operations goes. And they're all solving some different kind of problem. That's yours, by the way. So the question I want to cover in this tutorial is how do we connect planning and robotics in a way that can reuse some of the knowledge and some of the work that's already been done to create this wealth of systems that are available. It seems like a bad idea just to ignore the fact that they exist and start building your own task planning robotic architecture. The second point is you can't just take Sean's architecture and say, well, that's going to work for my problem, because maybe the problem you're interested in solving is a bit different. So how can you reuse this software without also restricting the shape of your system in terms of those boxes and arrows? And finally, how can you do it in the easiest way possible with the least amount of coding? And this was really my main goal, which was I didn't want to have to implement POP-F, interface to my planner POP-F a third time. Okay, the second minor disclaimer, this is aiming to be an accessible tutorial. That is, there is no way, even with 4 hours, for me to go into a great amount of detail on how do you react to unexpected events, or is this plan still valid? Each of these are big problems. What I'm going to do now is really talk about how to connect planning and robotics with these three aims in mind. The purpose of it being that you should be able to go away, watch the video, and follow the instructions, and be able to build a very simple task planning robotic system, run it in simulation, and start experimenting as soon as possible. The tools we've built for that we call ROSPlan, and we use them to connect PDDL and ROS. We chose this first because our group uses PDDL all the time, but it's also a standard language for planning. There's a lot of material out there for it, and on the robotics side, ROS is the same thing. It's one of the most widely used middleware for robotics. So that is, there's already a vast amount of third-party software that performs all the functions that you probably need on your robot, such as navigation and mapping and grasping. Okay, there's the asterisk here because over time it's extended to cover a number of different languages, including probabilistic planning with RDDL and PPDDL. This is the overview of the following tutorial. I'm going to explain a bit about ROS, what it is, how it works. Then I'll talk a bit more in detail about what are the different component parts of ROSPlan and how are they used. And I'll do some active demonstrations showing ROSPlan in action to give you an idea, and some examples at the end. Are there any questions before I move on, though? Okay. Who here is not already familiar with ROS? Okay, I see like a lot of kind of hand waves. So I'll assume that you're all partially familiar with ROS. And but again, just ask any questions if you have them. Okay, so ROS is, as I said, it's a middleware. It's a set of software libraries that help you build software for robotics. The way in which a ROS system is built is as a collection of nodes. Each ROS node is a process that should perform some kind of function. And these can be distributed amongst different computers, or they can be centralized. And then they communicate by passing messages. They pass messages over a TCP connection. If you are interested in knowing more about ROS, there are tutorials online. I put the link here in the slides in case you're going through these tutorials later and you realize these slides don't tell you enough about ROS. Go here, follow the tutorials, you'll know everything about ROS. They're great. Okay, so as I said, the nodes, they each run in their own separate program. Usually it's one process. You can make them multi-threaded if you want. But they are encapsulated as a node. They have a unique name, and they can be launched with different parameters, like program arguments. These parameters are all kept on a centralized parameter server. I think generally they're meant to be used for static values that don't change too much. For example, configuration options for your sensors. We also use them for the coordinates of waypoints, which we'll use in the model. Messages are the main way in which nodes will talk to each other. A message is a packet of data. You can define it like a C++ structure that will then be sent on topics. A topic has a unique name. Any node can publish to that topic, and any node can subscribe to that topic. When a node publishes on a topic, every node subscribed to the topic will receive that message. And topics are tied to a specific message type. So I think that makes a lot of sense. So for example, you might have this RGBD camera, so a Connect, publishing a depth cloud message. So the depth cloud is just an array of points, which are the depth of each point at each location. And face recognition might be subscribed to this depth cloud to read it as a 2D image and do some face recognition, or a collision avoidance system is subscribed to the depth cloud so that the navigation doesn't run into walls. In all my diagrams, nodes will be ovals and topics will be boxes with the arrow pointing in the direction of publisher and subscriber. Services are similar to topics. The difference is that they are more like a remote procedure call. only one node will be a server and will provide that service. Other nodes are able to call that service, and when they do, there is a message type for the call, which passes in parameters, and a message type for the response, which is then returned to the caller. Services are blocking. So when one node calls a service, the process stops until that service responds. Yeah?
Are the slides available now?
I don't think they're online yet. Do you want them so you can follow along at the same time?
Yeah. Then
Okay.
Careful.
If that's okay, can I upload them during the coffee break?
Yeah.
Okay. I will also, in my diagrams, use boxes for services, but I'll use a double-headed arrow to show that it's a service call. So an example service might be provided by face recognition that, when called, performs a single recognize action. These differences will become important later when it comes to updating the state. When you're performing observations, it matters whether or not you have a continuous stream of data published at some frequency that's updating, say, the position of the vehicle, as opposed to some one-shot observation that possibly has to be planned and placed into the planner's model. Okay, if you have ROS installed, I think the one person who did has gone away to give a talk, which will be back. Then you can try follow along with these. You will all have, from the first slide, there's a link which will give you all of these files, including this one I have open up here, which is the list of commands that I'm going to run during this tutorial. So you should be able to follow it line by line afterwards. So this is a very simple simulation of a robot in an arena. And this is the visualization that's usually provided, that's usually used in ROS, called RViz. So this is the robot model. The black and grey correspond to the static map. That's the map that's assumed never to change. These colours, faint colours here, are the cost map used by navigation. So when navigation is plotting a path, it's very cheap to move in these light areas. The closer it gets to walls, the more expensive it is. It's trying to avoid colliding with the walls. The green arrows around the base of the robot are localization markers. They're the robot's predicted position. Right now it's not very well localized. It knows that it's somewhere in this area and it's probably facing this way. Actually, that's not badly localized at all. So what I just typed there was ROS node list. So I made a list of the nodes that are currently running. So each of these is one of those encapsulated processes that's running. So for example, AMCL here is that localization process that's producing these arrows. CMD velocity mux is a velocity multiplexer. It's subscribed to a number of different topics which are telling it how the robot should be moving, and then it's combining them into just one command for the wheels. To see that one in a bit more detail, you can do ROS node info. And this tells you the name of the node, but also the subscriptions and services and publications that it provides. So all nodes publish to ROS out, which is just the debug stream. This one is also publishing to the mobile base nodelet manager, so that's it publishing to actually move the robot. And it's also subscribed to that. Essentially there's only the navigation is asking the robot to move, so the multiplexer is not really doing very much in this. Okay. Just to take a look at parameters as well while we're here. So the parameter server, we can also list them, has a large number of parameters in it already, any one of which can be fetched and changed. And we will use the parameter server later when we start looking at the ROSPlan nodes. So I changed the robot's name to Kenny instead of Turtlebot. For some reason, in our lab, most of the robots are called Kenny. Okay. We just had a look at that. So now I'll have a look at messages. Before I do, you might notice I've put a launch file at the top of the page here. In ROS, launch files are the most convenient way to start your program. It's an XML syntax definition of all of the nodes that you want to start running and what are the parameters for those nodes. So in this case, this is from the ROS tutorials. We have a launch file that's going to load 2 nodes from this package, and these are the executables, or in this case Python scripts, that are going to be run. These are the unique names that those nodes are going to get. If they're not unique, you'll get an error. So just like with nodes, you can list the number of topics, and you'll see there's actually quite a few going on. And we'll just take a look at one, which is the scan topic. So the scan topic has a type. This is the type of message that's going to be published upon this topic. It's called Sensor Messages Laser Scan. It's being published by Stage ROS. Stage ROS is not a camera that's actually scanning. Stage ROS is the simulator that's running. This simulator is very simple. It doesn't actually simulate any physics. It's just simulating the sensor data. And it's subscribed to by AMCL, so that's the one that's performing this localization. It's listening to the scan to try and decide where the robot is. Also to MoveBase, which is the navigation component, so that's the collision avoidance. And finally, it's being subscribed to by RViz, which is this visualizer. You see this red line is actually the scan topic. I think if I give it a little movement, then you'll see the red line moves as the robot does. And we can have a look at the scan. So the line I just ran there, ROS topic echo just prints the messages being sent on that topic. -N2 means only print the first 2 messages, because these are being printed at quite a high frequency. We don't want to have a look at all of them. And this is the scan. Just a lot of data, basically. And at some point, we need to figure out how to connect this to our planning model so that we can understand what is the current state. Okay. Finally, let's have a look at a couple of services. Services, again, very similar to topics. We can create a list of them, and there's usually very many, but a lot of them are about setting logger levels, and you can ignore that unless you work in ROS. So for example, this one fetches the static map. The static map is this black and grey map that's underneath everything. And you can see this is the what's returned. Okay. Finally, a very useful tool is RQT. You can launch RQT on its own and load plugins as you like. I'm just loading a single plugin, which is the node graph. The node graph is showing me all of the nodes that are currently running, plus all of the topics that are being published. And this is live. So if I can just see, here's AMCL again. And it's subscribed to scan. So here's the scan topic that we looked at. It's also being subscribed to by MoveBase over there on the other side, and being published by Stage ROS. So this is an extremely useful tool to see, well, what exactly does my system architecture look like? If you're very lazy, you can take a screenshot and then put that in your paper. guess now you're all ROS experts. Is there any questions about that before I move on? Is anything unclear? No? Okay. Good. It's fairly straightforward in the end. All right. So first, ROSPlan has a website as well as a GitHub page. The advantage of which is that there is also a set of tutorials for ROSPlan. Following these will be quite similar to the tutorial I'm giving today, except not as good, until we update them maybe. I just don't think that there's any way you can compare following a tutorial on your own to having someone shout it at you. Okay, so just going back to what I was talking about before, there is this wealth of system architectures, and we had already built two. When designing ROSPlan, the question we asked was, which components, which boxes are present in all of these system architectures? What are the interfaces, the nodes, that everybody has to implement, no matter what their system architecture looks like? And there are some wildly different system architectures. As well as that, what are the boxes which perform a single function? Which are the ones that you can't break down into smaller boxes with arrows? What we wanted to implement was, of course, all of the ones which are common to all the system architectures, because then we can just keep using them. Second, if it was not an atomic box, we wanted to break it down further, because the reason we were building ROSPlan is so that we could use it in future projects where we're interested in changing, for example, the plan execution algorithm, or changing the way in which we're generating problems. If the way in which we're generating problems is wrapped inside a node that's also doing a lot of other stuff, we're going to have to implement all that other stuff again. So we really wanted to make it as to make each node as small as possible to perform a single function. So I'm going to cover 5 of the nodes of ROSPlan, the 5 which I think are the common ones. There are a few more which we made just for our own use. They can be combined in a variety of different system architectures. I'll show you a demo which is a simple replanning loop, which can be used with this stage simulation for the robot to navigate around. And then, probably after the break, I'll show you some other ways in which these nodes can be combined to create different system architectures. For example, the one we used in Pandora for these long-term missions, where in fact there were many planning episodes and plans being merged. Okay. So this is an important point. When you download ROSPlan, there is an example launch file. You can launch it, and it launches the demo system. I think there was a picture of it. Here are some dots and boxes, some arrows and boxes rather. This is a system architecture for doing planning. But this is only one way in which these nodes can be connected. The purpose of this system is so that you can reuse these even on their own to replace the implementation effort that you might otherwise have had to do in writing your own system architecture. If you're someone who's really only interested in how is the plan executed, it's possible that you can in fact ignore implementing the rest, use ROSPlan and focus your attention on just what's going on behind this interface. Okay. Node number 1 is probably the most complex in regards to the purpose it serves in the system, but probably the most simple in the way that we've implemented it, which is the knowledge base. So the knowledge base stores the planning model. It stores the domain model and also the current state. When it's launched through parameters, ROS parameters, you specify a path to the domain file and to the problem instance optionally. If you don't specify a problem instance, then you have an empty current state in which all functions are undefined, there are no objects, and any Boolean facts are false. The knowledge base doesn't publish anything, as far as I'm aware, or subscribe to anything. It only provides services. And all of these services are here in these double-headed arrows, can be used to fetch different parts of the domain or the state. So it is a repository of your model. It, very importantly, doesn't perform any inference inside. It's not an ontology. It's not doing any reasoning. It's just like a database. Okay, so this is just covering what I said. Before the knowledge base loads the domain when it launches, and then you can call it services. So, for example, to fetch what are all of the instances of type robot, or what are the current propositions that are true with the predicate label docked, and it'll say, well, robot 1 and robot 2 are docked. And it can also be updated. So it has a service. The parameters of that service, that's the type of message that's used to call the service, contains all the information you want to update the knowledge base with, and the response will tell you whether or not that update was successful. Okay. The reason the knowledge base, despite being quite a simple implementation, is one of the most important parts of the system is that without this persistent state, you can't really perform planning. Planning requires a current state that's built from observations over time, as opposed to a purely reactive system. And this goes back to that assumption I was talking about half an hour ago. Okay. The second node, I'm just going to go through these 5 nodes quickly, and then I'll show you how to use them in a bit more detail. But the second node is this problem interface. The problem interface calls the services of the knowledge base to then produce a problem in a format that can be solved by the planner. This is sort of the most boring thing you would have to implement if you were building your system from scratch. As long as the node it's calling possesses or provides the same services as provided by implementation of the knowledge base, it doesn't know whether it's calling the ROSPlan knowledge base or some wrapper that's been built around an OWL ontology, for example. This is the advantage of ROS and having a modularized system. The problem instances that it generates can be written to file or published on a ROS topic. This is all specified by parameters, as we'll see later. So when you call the problem instance, the problem interface's service, it will then spit out a problem file. If nothing has changed since when the knowledge base was launched, it should be exactly the same as the problem file that was loaded into the knowledge base. But as time passes and sensors update the knowledge base, this will change. Okay. Another mundane node is the interface to the planner. This is just a ROS node which wraps around a planner to parse it, your domain and your problem, to call the planner with the necessary arguments, and then to publish the output from the planner. And we attempt to publish this in the IPC format of just the plan in a string form. We have planner interfaces now for 6 different planners, and fortunately a lot of them now do use the same output format and input format, which means there's quite a wide choice of planners available to be used directly out of the box. Okay, parsing interface is a bit more interesting. So the way in which your plan is going to be executed is through ROS messages, not as a string plan in the IPC format. So each of the actions is going to have to be at some point converted into a ROS message that can be published. The parsing interface performs this job. There's a message type, which is a PDDL action. I think there's also an RDDL action message, which contains all of the information that would be in your PDDL model for that action. So the action name, its parameters, its effect, its conditions. But the parsing interface also does slightly more than that, which is that it will collect those action messages together into a plan message, the structure of which depends on which parsing interface exactly you're using. We'll have a look at a couple. But in robotics, I think all planning is essentially temporal planning, even if you're not using a temporal model. When you execute it, it's going to be executed temporally. And if that matters, if you have time constraints, then you need a slightly more sophisticated way of storing your actions than as an array of messages. The plan dispatch is the most complex node in that it is a node whose function is to execute the plan by following some plan execution algorithm. And that plan execution algorithm is tied very closely to what is the representation of a plan we're looking at. If our plan is represented as an STN, then there are different plan execution algorithms which execute STN plans. If it's represented just as an array of actions with no temporal information, then again there are different execution algorithms to be used for sequential plans. So much like all of the other nodes, the plan dispatch provides a set of services which you can call, and one of them is please execute the plan as a method. The service will execute, and when it responds true or false, it returns whether or not the plan was executed successfully and also whether or not the goals were achieved. Okay. So here's the example launch file. If anyone does have ROS installed, didn't download all the files, you can type this really quickly right now. But this is the first tutorial launch file that I'll show you. This one launches a node, the knowledge base node, and also the problem generation node. And these say include rather than node, because what I'm doing is I'm including a pre-written launch file that just launches that single node. The reason I do that is then I have all of the parameters out with a default value in one place. Let me see what the next slide is. Okay. The parameters on the knowledge base here are going to load a domain that looks a bit like this. This is our sort of simple Turtlebot demo domain. We have two types. There are waypoints, there's a robot. There are 4 actions. The robot can dock and undock from its recharging station. It can localize, which is the function that will take all of those green arrows we saw earlier and hopefully compress them into one spot pointing in one direction, which means the robot now knows where it is. And the go to waypoint action, which, as I said before, removes the robot from its start waypoint and then adds it at the end of the action to its destination waypoint. And this one also has the effect that the waypoint that it's going to will become visited. Is anyone here not familiar with PDDL or needs more explanation of what the syntax is? That's good. Okay, here's the problem file that's going to be loaded initially into the knowledge base. Very simply, the robot's at waypoint 0 and docked, and the goal is that it must visit all of the waypoints and dock again. So it's about as simple as it gets. Let's take a look at the simulation. We may as well run it. That's already running. I'm going to close it. There we are. Okay. So this has just launched that launch file I showed you, just to make sure you get familiar with the output from ROS and you can follow along. When you create a launch, it lists all of the parameters that were launched, Many of these are inside the namespaces of the ROSPlan nodes. So for example, you have your domain and your problem path here. It'll also list all of the nodes that were launched. In this case, we just have these two. The ROSPlan knowledge base has been launched and the problem interface has been launched. And as before, I'll show you the different outputs from listing the nodes and the topics, and I'll show you how these can be used. So, as I mentioned, the different nodes often provide services that can be called. So here are all of the different services available from the knowledge base. There's a great many, but the four at the bottom here, by the way, can you read these okay? Yeah. Are to generate the problem instance. So I'm just going to call it. Okay. So from the output here, everything with KCL at the start is the output from ROSPlan, just so you can easily grep it. As I called the problem generation server at the bottom, there was this output from the ROSPlan problem interface. The problem was generated, which is successful. It was generated to this place. And let's just quickly go back here. Yeah, okay. In the parameters for the problem generator, you specify exactly where you want the problem file to be written. And in that case, it's this problem.pddl. So this file here is the one that was automatically generated just now. And you can see it does match the initial one. But probably more useful, we can also echo this topic, the -n1 meaning we only want the single message to be printed, and it's printed this problem instance. Okay. Let's move swiftly though onto planning so that something more interesting happens. The next launch file adds a third node, which is the planner interface, which has a great deal more parameters. Let's see. These first two specify the name of the topic to which this node is going to subscribe and wait for problem instances. So you can run multiple problem generators and multiple planner interfaces at once and decide which ones are subscribed to which topics. In this case, we have one problem generation, which is going to publish on this problem topic, problem instance, in its own namespace, and one planner interface, which is subscribed to the problem interface in the namespace of this node. Does that make sense? I know the namespace part might be confusing because I didn't really talk about it before. Okay. And there's this flag to say use problem topic is set to true. This means it's going to wait for a subscription, and it's not going to be able to plan until it receives a problem instance published on that topic. If that was set to false instead, it would read from file. And you can specify the problem path as a file instead. Probably the most important parameter here is the planner command. This is the command that's going to be used to run the planner. The example one is which is going to run popf, and it has these wildcards, domain and problem, where you can throw in the domain and the problem file. I'm running it with a timeout of 10, and I'm not running it with any optimization. So what that means is popf is going to return the first plan that it finds, as opposed to try any kind of optimization. So I expect to see an unusual plan. So I will run tutorial 2. No, 2. And take a look at the ROS graph. Okay. So the node graph from RQT doesn't show services. As a result, the knowledge base is sitting kind of on its own. It only shows topics, and we can see that the topic of interest, the only one that's got a subscriber and a publisher, is this problem instance, which is being published by the problem interface and subscribed to by the planner interface. And the reason this subscription is here is because of the way we set up the parameters. All right, so same as before, I'll call the problem generation, and we see that the problem was generated. We also see some output from the planner interface that says problem received. This is ideal, and we can call the service for the planner interface. So you can get the service names by looking through the commands file that will be part of the tutorial, or taking a look at the documentation on the website. Okay, so I called the planning server, and there was quite a lot of output after the problem was received. We saw that it wrote the problem to file. This is because PopF requires a file name. You can't take the data from the standard input. Ran this command. So this is exactly the command that was specified in the parameter, but it's replaced the domain and problem wildcards with the actual absolute paths to those files. And then it says planning complete, and the plan was solved. So this service returns true whether if the planner found a plan, or rather the response message includes a field that it should be true if the plan was solved. Okay. And I can publish the planner output topic. So again, this is just echoing the last message that was sent on this topic, ROSPlan, planner interface, planner output. We have the time and field.data, so this is the timestamp of the message, that's just a ROS thing. And then from this point on is the plan. So at time 0, undock, localize, go to a lot of waypoints, and dock. For some reason it's revisiting waypoint 0 after visiting any other waypoint, but I did mention I didn't do any optimization. This was just the first plan that was found by PopF. Okay. So I created this bash file. It's a very, very small bash file which simply calls those services I just called by hand. This bash file is the start of my top-level control, which could, for example, be a replanning loop, just calling all the services one by one inside a while loop. If I run this bash file, again, the problem is generated once more, and the planner is run again, and the plan was solved, and probably it will be the same plan. Okay, is there any questions about the planner interface? Any functions that you're wondering if it might have? Or is there something not clear about the way in which it works? Cool. All right, so now the more fun part. Let's start looking at plan execution. So I mentioned before that there are these two nodes. There's the parsing interface, and there's also the plan dispatch. And the parsing interface will take that, subscribe to that topic that I just printed to the screen, that list of action messages with the timestamps, and create a set of ROS messages that can then be published on different topics. The plan dispatch publishes to these two topics the action feedback and the action it subscribes to the action feedback and it publishes to the action dispatch. It does also publish to the action feedback. This is because sometimes the plan execution algorithm is checking, for example, are the preconditions of this action achieved, yes or no? And if they're not achieved, it publishes its own action feedback for that action saying, didn't dispatch, the preconditions weren't correct. And then probably it will return that the plan has failed. But that aside, these two topics will be the ones on which the action messages are passed to the rest of the system. So here is a new launch file which adds two more nodes. The ones above are the same as before. We're adding this plan parsing node and this plan dispatching node. And there are multiple executables which implement this interface, we're using the simple plan parser, which is going to create an array of ROS messages, each message being an action, and the simple plan dispatcher, which is about the simplest plan execution algorithm you can get. It will publish the first message in that array, wait for it to say that the action was successful, and then publish the next message. There's no concurrency and no other checking. Okay. So what happens when you publish a PDDL message? Let's hold on. Let's run that first before I forget. Okay, so this is the same launch file as before. And I really find that it's helpful to get sort of this bird's eye view of what's going on. So as before, there's the problem interface publishing the problem instance, and it's being subscribed to by the planner interface. The planner output now has its own subscriber, set up again by parameter, this parsing interface. The parsing interface is taking this string output from this topic and publishing a message on this topic called complete plan. And we'll have a look at that in a moment to see what it looks like. And that's being subscribed to by the plan dispatcher. And there's action feedback and action dispatch, and a bunch of other topics. Okay, so I'll run the simple script again. And now there's a new line at the bottom there from the parsing interface that says planner output has been received. So the parsing interface is ready to go. I can call it. And there's a couple more lines now. The parsing planner output, and from the ROSPlan plan dispatcher, plan received. So now the final node in that chain has received a message that it's ready to execute. So that was the plan. It is the same as before. The robot's visiting all of the waypoints, visiting waypoint 0 many times. And this is the output from the plan parsing node. So we've got a lot more space taken up in this message than in the other one. It's in this YAML format, which is, in this case, it's an array of messages, and each message has a sort of key value set. The action ID, the name of the action is undock, the parameters of the action, the parameter label V is Kenny, the parameter label waypoint is waypoint 0. Then it's got this duration and dispatch time. So it's robot Kenny is undocking from waypoint 0 as this action. And this corresponds to the first action in the plan that was produced by POPF. So essentially this is, and I can show you exactly the structure this is. This is the complete plan message. I've just shown the message on the screen down here. It's quite small. There's a comment that says complete plan message, and then it's an array of action dispatch messages. It's very straightforward. The -R there is just to show the raw format. If I don't include the R, then it expands what is the action dispatch message, which are just these parameters we saw: the dispatch time, the duration, the parameters, and the name of the action. Right. So now back to action interfaces. What do you do when one of these action messages has been dispatched? They need to be connected to some existing ROS library or to a custom implementation of that action. So this is the acting function from that list at the start. Probably there will be some kind of closed loop control that corresponds to that PDDL action, whose goal to achieve are the effects of the action in the model. So we have this message, go to waypoint, or undock Kenny from waypoint 0. It's in PDDL. It should be a simple matter to convert that message into a service call to some undock library that you've downloaded, but there are a number of issues that need to be considered just in connecting these two parts. So for example, in this go to waypoint action, in Rao's talk yesterday, he mentioned that in order to move, the robot first had to stow its arm for safety before it can move. How is that movement action actually implemented? If the arm only needs to be stowed for movement and always needs to be stowed for movement, maybe it's not in the planning model, it's just part of the way movement is implemented. So rather than connect this single go to waypoint PDDL action to a single service call to a navigation planner, instead it calls the stow function first. It waits for the arm to be stowed successfully. Maybe it retries that a few times. Then it calls the navigation, and at the end of the navigation it unstows the arm. That's not a process that could be easily automatically generated, this connection. Second, what are the coordinates of the waypoint it's going to? Here it says waypoint 9, but the navigation planner doesn't know what waypoint 9 is. It requires you to call a service, and the input to that service perhaps is the exact coordinates you want the robot to move to. So you have to first of all replace go to waypoint 9 with the lower level description of move the robot base to this position. And at what orientation? Usually you need to require an orientation for that robot. This might not matter. You might just want to go to the right position, but if you want to dock, you probably have to be facing the recharge station in order to dock with it. This action message doesn't include what is the next action in the plan, and probably it shouldn't. But then what is the orientation that the robot's supposed to go to? That waypoint where the recharge station is might also be the same waypoint where the table is, where it picks things up. Do you want to then have a different waypoint for each different task that the robot might have to perform, or for each different orientation that the robot might have to be at that waypoint? All of these three start asking questions, not just about how to connect the PDDL action to the lower level control, but also how should the domain be modeled? Why not just model whether or not the arm is stowed or not? But then again, why not just model the exact coordinates of the robot and the orientation of the robot directly in the PDDL? I mean, why not is because then you'll never be able to solve the problem. You have to make some kind of abstraction. You have to make it simpler. And this is where you pay for making it simpler, because when it's time to actually execute those actions, you have to make them complex again. And the way in which you make them complex can be tricky. Going back to this third one, a very nice example of this is why is planning useful is this scenario I've seen before of cans on a table that the robot has to pick up, but there are many cans obstructing the one in front of it. One solution, the robot might be able to have two different grasps, one where it grasps from the top, one where it grasps from the side. It could probably grasp from any angle. All you need to do is call the move it, the motion planner, please put me in the, please grasp this object, and it will figure out how to reach around the cans and take the can. But if the next action is to put the can on a shelf and the hand is blocking it, then the only way to grasp the plan and then grasp the can and achieve the next action is to grasp it from the side and move it into the shelf. The grasp planner doesn't know that. It shouldn't have to know that the next action is to put it in the shelf. But maybe it should know that there are some constraints on the way the can has to be grasped. If those constraints are going to be passed to the grasp planner, they either need to be in the PDDL model or they need to be here in this interface between the PDDL action and the lower level control. And then you can move into more complex things such as, does the action have its own timeout and can it be preempted? So now we're moving into what happens if there is an unexpected event, the plan's not being followed correctly, or we want to start following a new plan. Can we cancel this action halfway through? Yes or no? The answer is sometimes no. I mean, technically you could, but just the interface for it isn't there. And that will have a big effect on how this action is actually executed. Oh, I didn't quite have room for a single list. So there's one more consideration, which is this. Are all the effects of the action possible to sense? This obviously has huge impact on a later part of this tutorial, which is on how the knowledge base is updated from the sensor information. Because if you can't sense a part of the state, then you have to get that from somewhere else. This is that somewhere else. If you're executing an action, push the button, and there's no sensor that allows the robot to know whether or not the button has been pushed. One thing you can do is to say, well, I did the action returned success, it said that the arm completed the motion. I'm going to update the knowledge base and say that the button has been pushed. It's not unreasonable. It's done in navigation all the time. For example, in the autonomous underwater vehicles we had, they would look at the ground and see the speed of the ground moving underneath them and say, well, roughly I'm moving in the direction I'm supposed to be moving. I'll just update my position until I find some landmark to better localize myself. This is dead reckoning. If not all of the effects of the action are possible to sense, you have to use dead reckoning and assume that those effects have been successfully achieved. Okay, so there's actually a lot that goes into just connecting a single action to the lower level control. But in essence, you want to subscribe to the PDDL action topic. You want some node to subscribe to that, to perform this kind of reasoning and call the lower level control. And optionally update the knowledge base with the effects of that PDDL action. We have one node called the ROSPlan action interface, which does most of this. That is, it subscribes to the topic, it checks the action name and the parameters to make sure that they're all correct and that they're the action that's supposed to be executed by this node. It updates the knowledge base with action effects, and you can flag in the knowledge base which parts of the state can be sensed or not, and the node will only update the parts which can't be sensed. It subscribes to it's actually the same topic, the action dispatch topic, to monitor whether or not the action has been cancelled. It doesn't actually cancel the action, it just has a flag which says the action has been cancelled. And then it calls an abstract execution method. So this is an abstract class. You can't actually launch it. It's meant to be extended to implement this method, which will actually call the low level control. We have a couple of examples of an extension of the action interface. And then finally, it returns the action feedback, action success, or action failed, generally. So one example we have for the action interface is the one which calls our navigation planner. So this is what we'd call the move base interface. It subscribes to the action dispatch. It will then update the knowledge base with the start effects of the action, fetch the waypoint coordinates from the parameter server corresponding to the waypoint in the PDDL parameters, and then call MoveBase with that coordinates as a goal. It'll monitor MoveBase while checking this action cancellation flag. MoveBase can be preempted. You can tell MoveBase to stop going to a waypoint. So if that flag becomes true, it'll preempt the action and respond when the action is complete, preempted or not, on the action feedback topic. So some of that is very specific to MoveBase and is implemented in this abstract method. And some of it is just part of the interface. Okay, so to the launch file, after dispatching, I'm adding 1, 2, 3, 4 nodes, one for each action: dock, undock, localize, and go to waypoint. And the node that I'm launching is called simulated action. I don't know if I've got a slide on that. I do. So simulated action extends the action interface, and inside that concrete execution method, it goes to sleep for an amount of time. It basically does nothing. You can set in its parameters the probability with which it returns action success or action failure, and you can also set in the parameters the duration or a distribution of the duration for the action. So if you're very interested in testing a planning system, but you're not interested in running a whole simulator and having it take up a lot of time, these nodes will just very quickly tell you whether or not actions succeed or fail. So let's just test them out. Okay, so this is the same as before, the same chain of nodes, but now at the end on this dispatcher here, we have these 4 interfaces, and they're not publishing or calling the service of any actual lower level control. These are the simulated actions. So they'll go to sleep for some time, and then with a probability 100%, that's the parameter it's set, they'll publish on action feedback to the ROSPlan dispatcher that the action has been success. Okay. Another function of these actions is that they will also periodically publish all of the parameters of the action. That was important, but I don't remember why. Okay, I've extended the bash script, so now it calls the problem service, the planning service, the parsing service, and also the dispatch service. So that's the 3 I called before, but now we're also going to call the dispatching service and dispatch the plan. Okay, I have some more exciting plan visualization to show you in a bit, but right now I just want to show you this part. Here in this big block of text, you can see that that's the planner line again, and planning complete, plan was solved. Planner output received, parsing plan, plan received, dispatching plan, dispatching action, and this is the first action, undock Kenny waypoint 0. And then from the undock simulated action, we see that the action has been received, and the knowledge base is removing the fact docked, and the action is completing with probability 1. So this is just output from the simulated action saying that it's doing it. About 10 seconds later, it said the action completed successfully. Was it 2 seconds later, more like? And the feedback has been received, action achieved, and it's beginning to publish the next action. This is localize. Localize takes 60 seconds. So I'm just going to, oh, that was 60 seconds. I'm just going to kill it. We don't have to wait for this whole plan to execute. I'll save that for when I've got a much more graphical plan illustration. Okay. So the example system, we're almost there, really. We're running the knowledge base. We're running the problem interface, the plan interface, the parsing interface, the plan dispatch. On my diagram, I'm also showing the services that are being called. But this is basically the same node graph that I showed you running from that launch file. If you download ROSPlan, launch the example system, this is the system that will be launched. Okay, but we can make it a bit better. There's one difference between the example system you'll launch from our ROSPlan demos package, and that's we don't use the simple plan parser and the simple plan dispatcher as the defaults, mainly because they're just not very good for robotics. Instead, we launch what we call the STRL plan parser and plan dispatch. So this is a plan dispatch that's actually able to execute plans with concurrent actions and temporal constraints. So while the simple plan dispatcher simply has an array of actions, the STRL plan dispatcher the plan parser will first of all take this and construct the underlying STN that corresponds to that plan. And I'll show you an example of that in a moment. This is almost the algorithm that we use in the STL plan dispatcher. So this is for SDNU dispatch. Again, the references are all at the end of these slides in case you want to read. This is an STNU in which we have different time points need to be executed, links between these which specify ordering constraints with upper and lower bounds on time that must pass. And this dark one here is a contingent link, which is B is going to happen after A between 100 and 150 seconds, but this is not controllable. And this corresponds to the duration of most actions on a robot. When I say to the robot, go to waypoint A, I know that it's going to try go there. My PDDL model says that it's going to take 136.44 seconds to get there. In the real world, it's not going to take that. It's going to take some time to get there between an upper and lower bound, which I might be able to estimate. This algorithm, given the set of all the control points and the current time, picks a control point that is live, that is, it's enabled by all of its incoming edges. The method we use to pick it is we just pick whichever one is live and first in the plan that was produced by the planner. Set its execution time to the current time, update all of the edges, and propagate the constraints, and halt if the STN is now empty. That is, there's now a negative cycle, so there is no assignment to the remaining control points, which will satisfy all of the contingent links and boundary constraints. In brackets here, the propagate constraints part, our plan executor doesn't actually do yet, which means that sometimes it might continue to execute a plan that is no longer temporarily valid. This is work in progress. Finally, it basically loops back. It just advances the current time. But I find that in robotics, time has a habit of just advancing itself. Okay. In addition to this, there's a couple of extra parameters we included for timing out actions. This is because a lot of problems don't actually have a deadline. They don't have a temporal constraint. The one that we're looking at doesn't. We're asking the robot to visit all the waypoints and dock again. We didn't say before 3 p.m. Move base by default has got a timeout, but some actions don't. And if we start executing on the board the robot, we don't want it to enter some sort of infinite loop of retrying to grasp a can. At some point we want to give up. Well, I do. I mean, maybe you don't. And that's why these parameters are here. You can set timeout actions to equal true, and then even though the plan is still valid, temporarily valid, the action has taken too long and it's going to respond failure. And when the action returns failure, the plan will return failure. And you can also set an action timeout fraction. So rather than time, if this is set to 1, then the executor will time out the action as soon as the duration as specified in the PDDL is passed. If you want to give it instead a lot of slack and say, okay, if it's taking 5 times longer than the PDDL estimated it would, cancel the action, fail the plan, will replan. So you could set that to true and 5 and then make your system a little bit more robust. Right. Okay, we have a few other ways of executing plans, but really this is just to illustrate the purpose of ROSPlan that I mentioned before, and that it should be possible to replace any one of these components, or even use just a single component on its own to replace some integration effort that you might have otherwise have done. I don't think that's the right citation, so I'll fix that. But this is, oh no, this one is correct. So this is the RMPL language for representing a plan. We're actually now working on a plan parser which will take the PDDL output and try to construct an RMPL based representation of it. One thing we have already done, this is the one I was thinking of, is the PetriNet planning. So in PetriNet planning, the plans are represented as a PetriNet in which actions start and ends are, instead of being control points in an STN, are places in this PetriNet, guarded by these gate conditions. And Luca Iocchi, who gave the talk yesterday, worked on this with execution rules, where you can generate the PetriNet corresponding to the plan produced by your planner, and then combine it with some small execution rules that were written by hand, such as if this action takes longer than 5 times its duration, then return to waypoint 0. So some of those, how to recover the state, could be hand coded and then compiled into the plan to produce a more complex PetriNet that you can then just execute. Okay, let's see. I believe I have the launch file as before. So this is the new launch file with the better plan execution. So this was the complete plan message that was used before. This is the new plan message for the STRL plan. It contains 2 arrays, an array of nodes and an array of edges. If I just expand that, each node can represent an action start, an action end, or the plan start, and has a node name, but also within it, it has an action dispatch. So every node represents, apart from the plan start, the start or the end of an action. Even the instantaneous actions in PDDL are represented as a start node and an end node, because in ROS anyway, there's no such thing as an instantaneous action, because every action takes at least the amount of time to publish the action start and to subscribe to the action response. And that's going to be a few milliseconds, but it's can be important. Between these nodes, there'll be edges that represent these ordering constraints. Each edge has a duration lower bound and a duration upper bound, and they have a different type. Many of them are these start-end action edges, which go from the node which begins an action to the node which ends an action. There are also edges which represent causal support. So if one action has an add effect, which is or any effect, which is required to satisfy the precondition of another action, there will be an edge between those 2 nodes to say, well, this one must come after this one because it relies on it. And the last type of edge is the interference edge, which is the planning PDDL concept of mutual exclusion between actions, or violating invariant constraints, in which if there is an action which deletes the condition of another action, then it has to be ordered either after that action completes, or before the causal support of that action is completed. So that is, we don't want it to delete the condition of the action before we have a chance to do it. Similarly, if there's some durative action with an invariant constraint that can't be violated between the start and the end, if there is a node which has an effect that deletes that invariant condition, we need to make sure that it's ordered after the end point of the durative action or before the start point of that durative action. So you end up with these interference edges. All of these edges are generated from the PDDL domain problem and plan by the plan parser and populate this message, which is then sent along. Okay, so I'm going to just call exactly the same script as before. That's the tutorial4.bash, which is going to call the problem generator, call the planner, call the plan parser, which will generate all these edges, and then call the plan dispatch. This time it's the STRL dispatch, and the STRL dispatch produces this. Okay, so this is the terrible plan. Here's the same output as before, and this is these are the start and ends of each action. There is a flag I set to true which will color the edges so we can see what kind of edges they are. The red edges are the action start and end. So here we had to go to waypoint start, Kenny waypoint 0 to waypoint 2, go to waypoint end, Kenny waypoint 0 to waypoint 2. The blue edges are causal support and the green edges are interference. I may have gotten that the wrong way round. If this had been my implementation of it, I would have definitely made the red edges interference. Okay, this plan's already finished. I reduced the time of the simulated actions there so we could see it going. But we should see dispatch complete here. Okay. Let's see what the time is. Does anyone know when the break is? It's 10:30. Thank you. Okay, that's no problem. All right. So the last node to look at is knowledge base. Yeah, sorry.
Forgive me if I a stupid question. I wanted to know your dispatcher.
Hold on, shall I give you this? I forgot I had this to give to people.
It's for the camera.
Yeah.
All I wanted to know was if your dispatcher can handle. So currently, you said it can handle Estro plans, and then what about you showed RMPL or PetriNet plans? Can they dispatch?
So we have a different implementation for PetriNet plans.
Okay.
Which means you end up with two executables. One is the STL plan executable, and one is the PNP plan executable. You can launch either one. They have exactly the same interface. That is, they have the same services and the same publications and topics. So you should be able to switch them quite easily, with one exception, which is that the plan parser needs to pass the plan into STL or into PNP, because they expect the message type of the complete plan message to be different.
Mm-hmm.
But otherwise, those are both existing, as well as the simple plan. We don't have an RMPL plan execution yet.
Okay.
Any other questions about plan execution? Okay. Let's talk about updating the state. And this will then sort of close the loop for a very simple system. So the knowledge base, you can fetch any part of the state you want. It's also got these three services over here: query state, which will return true or false if you send it, a bunch of state information. It'll tell you whether or not that's true in the current state. Update, you send it a bunch of state information and it will write that into the current state. And clear, which just empties the knowledge base. How to update the knowledge base? There are three main methods for task planning robotics as I see them. The first is by action outcome. This is what I was referring to before as dead reckoning. That is, action dispatch has reached some action interface. It's going to do some lower level stuff. It's going to move the robot and make things happen. But it's also going to update the knowledge base with the effects of that action. It knows the effects of the action because it can read the domain from the knowledge base. It can say what are the operator details, and just at the beginning update it with the start effects and update it with the end effects. The problem with it is that if the controller doesn't do exactly what you expect, this is where you'll start to diverge from reality. But if you can't sense the data in any other way, then it's really your only choice. You also have active sensing. So active sensing is, we're going to make an observation now. It's a one-shot observation, maybe a service I'm calling, and the response will update the knowledge base. Often an active sensing operation will be something that's included in the plan. So it might correspond to an observation action if you're doing contingency planning, for example. So as an example of an active sensing action in the Squirrel project, once the robot did get into the room, it was able to look at the scene, take the image and perform segmentation, which was to basically put a different colored box over everything it thought was going to be a different object. So we'd say, okay, let's do that. Perform the action segment. And as a response to calling the segmenter service, it would respond with a list of objects, and we would enter those into the knowledge base as a new list of PDDL objects, updated with waypoints and positions. This was quite computationally expensive, so it's not something you want to run all the time, but something you want to plan to do. And in contrast to that, passive sensing is something that's probably not so computationally expensive, and you can just do it all the time. So the localization by AMCL is passive sensing. It's reading that scan data, trying to match it to the map, and publishing this cloud of points with orientations, those green arrows on the visualization. And it's doing this all the time. It's publishing with quite a high rate. So we can just have a single node which subscribes to the output from, for example, AMCL, and decides whether or not the position of the robot, the estimated position of the robot, has changed sufficiently enough that now it's changed also in our PDDL model. If this is one waypoint and over there's another waypoint and the robot's beginning to move, at some point the passive sensing will update the model and say, okay, we're at this waypoint now. Okay, is there any questions about these three?
How do you, I guess, control access between, if you have a passive sensing and your action interface, you might get conflicting updates to a variable based on your dead reckoning facts?
Yeah, I would say that if you have passive sensing of something, you probably shouldn't use dead reckoning on it. So like if we already have a sensor that's publishing at 10 hertz and telling us whether or not the button has been pushed, and we perform the action, push the button, the action interface shouldn't update the knowledge base saying the button's been pushed now. That's the job of the sensor, because we trust it more than this one.
And so that in terms of determining whether the action is complete, you're relying on the dispatcher to see that change.
Yep.
In that case.
Yeah, okay. I didn't mention there was no edges corresponding to it, but the dispatcher is also checking the knowledge base to see if the preconditions of the actions are achieved. This is what makes the STRL slightly different from the STN, is that there are another set of edges invisible in the graph which are coming in from the knowledge base, and each one corresponds to a condition on the node that it's touching. But I just wanted to muddy the waters a bit more. Let's say your passive sensor that tells you whether or not the button has been pushed isn't 10 hertz, it's 1 every 10 seconds. And we have to push the button within 7 seconds. Now do we want to update it when the action says I've pushed the button successfully? Shall we update it immediately, or shall we wait for up to 10 seconds to see if it was successful? Now it begins to get to the part where you thought you had a good model and you thought you had a good system architecture, and you start to have to put in some hacky solutions again. I'm not sure what the answer is. Whether it would be, in an ideal world, every part of the state would be covered by only one of active sensing, passive sensing, and dead reckoning. And if you can keep it that way, then you're solving a nice problem.
And that it also presumes, as far as the sensing side of things, you're translating complex world model or data, interpreting that through some kind of model to abstract, like a fact, like being at waypoint 1. You have to define what waypoint 1 is. It means within the radius so much, compared to your coordinates that you're actively moving, for example, or deciding whether something's open or closed.
So you're talking about how accurate is the model to the real world? What kind of abstraction is in that respect? I say I'm at waypoint 1. Actually, I might be 3 meters away from waypoint 1. There's also how accurate is the sensor? If I'm just using a neural net to decide where I am based on what a 2D camera can see, then my being at waypoint 3 in the PDDL model might mean I'm probably within 3 meters of waypoint 3, and then according to the sensor, with a probability of 80% less. But That's what replanning is for. Okay, you had a question?
So, knowledge base, you said states that one, is that all the states, or you have states down there too? That down there, the local states, or I mean?
So these are the service names. So they're all calling the same service of the knowledge base, but the state is just stored here. Our implementation of the knowledge base only stores one state. You can just launch multiple knowledge base nodes, though, if you need more than one state, more than one domain. And I have an example of that after the break. Okay. In much the same way as there is an action interface that can be extended just to make connecting a PDDL or planning action to low-level control a bit less arduous, we also have a sensor interface node, which is aimed at just making this process of subscribing to a topic or a service and updating the knowledge base a little bit easier. Differently from the action interface, which has a single node connecting each PDDL action to its low-level control, the sensing interface consists only of a single node which can subscribe to many different sensor streams and call the knowledge base itself. So you only need to run one sensor interface node. And it's not one of the 5 core nodes I mentioned in ROSPlan because it's probably not applicable to all cases, but I do want to show you it in a bit more detail because it's one of the things that can save some of the most integration effort. So here is a new launch file that I'm going to run. Domain path, problem path are the same as before, same problem. I'm going to just launch the knowledge base, and I'm going to also launch this node, the sensing interface. It takes a parameter called main rate. This is the rate in hertz at which it will update the knowledge base. Essentially, you want this to be as high as you can while not killing your processor. And it's also going to load a configuration file. I'll launch it and then I'll show you the configuration file. So we're on to number 6. No, we're on to number 7. Oh, 1, I see, using 1. Okay. All right, here are the services available to the knowledge base. I grepped domains, that's why it's in red there. So you can fetch being that this knowledge base is a PDDL knowledge base, we have functions, we have predicates, operators, the domain name, the domain types, and you can also fetch operator details and predicate details. I'll quickly call these and show you the kind of output you get. So if I call types, we get 2 arrays back, a set of types, waypoint and robot, there were only 2 types in this domain, and a set of super types, where with the same number of items, and waypoint and robot don't have super types, or their super type is object. The predicates in our domain are returned like this, as little domain formulas. So we have an array of predicates. Each predicate has a name, for example, robot at, and then a set of typed parameters, which is label, value, label, value. In this case, the values are the types, because we're looking at the domain details. Okay, and just in the final example here, you can see the details for the go-to waypoint action. In the go-to waypoint action, you have the same formula as a predicate, so the name of the operator and its parameters. But then you also have its many effects and its conditions. And this will include details on probabilistic effects, sign effects, continuous effects if you're in PDDL 2.1 or above. And in the conditions we have start, end, and overall conditions for simple conditions. This is a fact that must be true. Negative conditions, and also comparisons between numeric expressions. Right. Let's have a look at the state. So these again are the services that the knowledge base provides for calling the state. Functions, except this time not the domain functions, but now we're looking at the primitive numeric expressions of the current state. The current set of instances, the current goal, and the current metric. The metric will be a numeric expression with either maximize or minimize. I think those are the only options in PDDL. The set of propositions which are true, and timed knowledge, which is the timed initial literals and timed initial fluents in the domain. This is something I didn't mention before, but in the knowledge base, when you update the state with a collection of, say, propositions, you can include a timestamp at which those will become true. This is the way timed initial literals will be stored. This means that that's not true right now in the current state, but at that time it will become true, and the knowledge base keeps track of that, just with a simple timer. This is used mainly when you're reading a problem file, and the problem file includes some timed initial literals, such as at time 100, the valve is open to be turned. So some proposition, valve open. We've also sometimes used it in active sensing. So when we sense, for example, is the door open, we add to the current state, yes, the door is open. And at time 100 seconds from now, delete that fact. We don't know it anymore. Okay, so this is just to remind me what the problem looks like. There are 4 waypoints and those goals. And I'll call some of these services. So when calling the get current instances, we just get an array of object names. There's only one robot, and his name is always Kenny. He was named by kindergarten children. You can fetch their waypoints, current predicates, current propositions, passing in, so this is the parameter that I'm passing into the service. It's a message type that's just a string, robot at, and the response from the service is a set of attributes. These are the knowledge attributes of the current state. Which is a strange phrase, but I'll show you what that means in a moment. So in this case, we have that robot at with v Kenny waypoint 0 is in the knowledge base. Its is negative is false. So we have a proposition which is true in the knowledge base. Okay. And you can pass in an empty string to the predicate name, and it will return the entire initial state here. So we have that docked is also true, and the dock is at waypoint 0. And finally, we can fetch the goals. But now let's look at updating the state with this sensor interface. So I mentioned a knowledge attribute. The way in which the state is updated is by passing these messages called knowledge item, or knowledge items. Where is one? Here we go. So when we call this service with ROS knowledge update service, you call with an update type. Either we're adding knowledge or we're adding a goal, we're removing knowledge, we're removing a goal, we're adding a metric or we're removing a metric, and then an array of knowledge items. And each knowledge item represents a part of the state. It could be propositions, functions, objects, instances, a number of different things. And I'll show you what the knowledge item looks like. But this is the sort of key part of the knowledge base. One knowledge item represents either an instance, such as Kenny, a fact, such as Kenny at waypoint 0, a function, I know Kenny battery is 100, an expression, which is a numeric expression, such as well, battery charge or 10 times duration, or an inequality, which is two numeric expressions and a comparison operator, such as battery charge is greater than 100, or duration times 5 has to be less than charge rate. This parameter, or this field of the knowledge item, specifies which type we're looking at, and then you can simply fill in all of the details underneath. So for the attributes we're looking at, robot at waypoint 0, we would set this to be a 1, or rather we would set it to equal knowledge item.fact, and then set the attribute name to be robot at, and this key value array to be the parameters of the proposition. And this message definition is how we update the state by sending these. It's also the form in which the state's returned whenever we call these services. Before I get rid of it, is there any questions about this? I mean, there's a lot of different fields there, and we don't want to go into actually programming anything right now, but are there any obvious questions that you have? All right, so I'm running now the sensor interface. And before I mentioned, so when I ran the sensor interface node, I specified a YAML file. So this is the configuration file for the sensor interface. This is the whole YAML file. It's through this that I will specify how the different topics that are being published in our system are going to correspond to state updates. And the first we'll look at is this. So there is a localized predicate in our domain, and this configuration file says that the localized propositions with the parameter Kenny are going to be updated from this topic called localized mock, which, by the way, is not a real topic. I would normally update this from something real, but this is just an example. The message type is standard messages Boolean, and the operation that's going to be performed on this message is message.data. That is, if the Boolean message.data equals true, then localized Kenny equals true. And if it equals false, then it equals false. The sensor interface has already read this configuration file, subscribed to the topic, and is ready to update the knowledge base. I wonder if I can show you that. There we are. Okay, so the knowledge base, again, services aren't shown here, and the sensing interface is calling the knowledge base service at a rate of 10 hertz. It's actually only going to call the service if there is something to change. And it's subscribed to this localized mock topic. All right, so I'm going to publish now from here. On the topic, you can publish messages from the console as you would from a node. And I'm going to publish on the topic standard messages bool, data equals true, and the -1 means I'm only going to publish the message for 3 seconds at some ridiculously high rate. And as soon as I did that, this popped up here, adding fact, localized Kenny 0. So Kenny is now localized. That's been added to the current state. If I call the knowledge base get predicates, then I get this predicate name localized. The key is P0, which is not actually the label, but it doesn't matter. And the value is Kenny. Right. Should that topic ever publish false, then here it's set the fact localized Kenny is negative equals 1. So it actually does this instead of simply removing the proposition. It sets it to be explicitly false in the knowledge base. This is because the knowledge base is also used, we use it for contingent planning, where each piece of knowledge can actually be true, false, or unknown. And you require observation actions in the plan to learn facts before you can execute the plan. But
in that case, the unknown is there's no fact.
there's no fact there, yeah. And when you generate your problem file it's a form of PDDL for contingent planning. The initial state will include propositions which are true. It'll also include propositions which are false with the not tag, and some other constraints formula such as one of these must be true. So it might say one of robot at waypoint 0, waypoint 1, waypoint 2, waypoint 3, waypoint 4. We know it's somewhere and only one place. In regular PDDL, if a fact is not in the initial state, it's assumed to be false. You just list what's true. Whereas in this variant, if it's not there, it's unknown. It could be true or false. Okay. Let's just call this one again. So I just set it to false by publishing the service, and you can see now localized is here and is negative is true. Okay. Okay, so docked and undocked. This one's actually the real one. Docked with parameters Kenny and parameters Kenny. You can also put a wildcard here. I think there's a version of that down there, so you can have this for every robot. But in this case, we have one robot. Its name is Kenny, and it's subscribed to this topic here, mobile-based sensors core. This is part of the Kabuki ROS packages, which are specific to the Turtlebot we have. And this message is published continuously with a whole bunch of information about the robot base, including one of the fields of the message is message.charger. And it has two states that I'm interested in, discharging and I can't remember what the other one's called, charging probably. And the operation that we're interested in is message.charger doesn't equal discharging, means it's docked. And message.charger equals message.discharging equals true. And if you turn on the robot, it's in the docking station, it's already publishing these messages all the time. If by hand you grabbed it, you lifted it out of the docking station, this message would change. It's reading the actual state of the battery, and using that, we're updating the current state in the knowledge base. So I can actually publish it from this tool, which is part of ROS. So I go to Sensor Data Core, and what was it called? Let me see again. Should remember. It's sensor state, so it's this one. Here it is, and here is charger. I don't know if you can read that text. It's not too bad. So this one says charger underneath the mouse, and it's currently publishing 1. As soon as I check this box, it will begin publishing at a rate of 1 Hertz. So I'll just check it. And it's now publishing. And down here we had a little warning saying docked Kenny already exists. So the sensor interface just tried to set that to true. Actually, it's already true. But it did also add the fact undocked. That wasn't in the initial state. That's probably a modeling error on my part. So it's updated the knowledge base to say that this fact, docked Kenny, is true, and this fact, undocked Kenny, is explicitly false. You can see here that is negative is 1. It's still publishing, so I'll set it to 0. 0. And immediately it pops up down here. The knowledge base has printed that docked is negative now equals 1, and the other one, undocked, is negative equals 0. So these have switched. If I generated the problem now, the robot would already be undocked. Okay. Some nice output from that. Okay, let's take a look at this one. A bit more complex. So again, I'm interested in robot at proposition. And in the sensor interface, you can link one predicate name to actually a number of propositions by adding wildcards into the parameters. So this block here is only interested in robot at with the first parameter Kenny, but the second parameter could be anything. The topic is the AMCL pose. That's those green arrows again. It's publishing an array of coordinates and orientations. And the message type for those is pose with covariance stamped. Stamped just means time stamped, essentially. There is no operation here. The reason there's no operation is instead it's going to look inside this reference to a Python file called functions. And you can always, in the sensor interface, specify one or more Python files which implement the function that's going to be called whenever this topic publishes a message which will be of this type. It will be passed to a function in that file with a name that matches the predicate. And this is the function. I don't want to go far into what the actual code does, but it's extremely simple. It finds the current location of the robot by calling the knowledge base. In the knowledge base, the current says the robot's at this waypoint. It finds the closest waypoint by comparing the different waypoint positions with the X and Y positions from the message. And just finds the closest one. Then if its current waypoint is not the closest one, it updates the knowledge base. It appends to the return value that this should be set to false and closest should be set to true. This is pretty flexible. You can write whatever you want to inside the Python script, and the integration effort it's saving you is having to write also the ROS subscriptions, the knowledge base updates, populating that knowledge item message. You can focus on just what's important. Okay, let me run this. Okay. Let's see. Okay, I think I already touched on this, which was questions such as where was the robot doing the action? And when can the other robot move between the shells? We had a conversation already about what happens if the navigation action fails in the middle of execution. According to the PDDL, the robot's no longer at the start waypoint and it's not at the end waypoint, so the robot's nowhere. That function I just showed you in Python is one fix to this, where the robot, it's always going to be somewhere, because we just take the closest waypoint and say that's where the robot is, and we just take straight line distance. That might not work for every problem, especially if the robot's supposed to be at a waypoint that's on the other side of a wall. We don't take that into consideration. But it's going to work for this example. So I'll run the one that I showed you from the beginning. This simulation. Let's just get rid of that. Oh, I should have closed RQT, I guess. Let me just open it myself then. Office. Sorry, I thought that was already included in the launch file. Alright, so here's the robot. Oh, it is included in the launch file. I'm running the wrong launch file. So I thought I'd be able to get through the whole first part without making a single mistake. And then Tim walked in. There we are. We're here. That's much better. Okay, so now we're running everything. I can show you the node graph once more before I run the... So this is the node graph I showed at the beginning with move base connected to the scan topic somewhere. And AMCL is running. And there is also now the ROSPlan nodes inside here. So we have the ROSPlan parsing interface here, publishing the complete plan, subscribed to by the plan dispatcher. Action dispatch is coming up here. These three actions, localize, undock, and dock, they're still being simulated. But one of them, all the way over here, is now being subscribed to by MoveBase. So MoveBase is no longer being simulated, but we're using that action interface I spoke about to connect it to the go-to waypoint action anyway to MoveBase. So let's just run, or let's move the robot. The sensor interface is running. So if I ask the robot to move over here into another room, see a bunch of output. ODOM received, got new plan is referring to, MoveBase is publishing these messages. This is referring to the navigation plan, the path. At some point, I think as it was moving through the door, we got a couple of messages from the knowledge base setting robot at Kenny waypoint 0 is negative equals 1, and robot at waypoint 1 is negative equals 0. So the position of the robot's now changed in the knowledge base based on this sensor interface subscribed to the AMCL topic. If I move it back, then about as it moves through the door, here we go, we get those messages again. Now setting waypoint 1 is negative 1 and waypoint 0 is negative equals 0. Okay, let's hide the text. We don't need to see that. And instead we'll run that bash script which will call all the services once and show the plan. Okay, and by the way, this launch file does have the optimization flag on popf, so we get a slightly more sensible plan. This action, I can zoom in a bit. So here we have go to waypoint 0, waypoint 1 is currently under execution. Then it's been succeeded, and the robot's off, moving to the next waypoint, waypoint 1 to waypoint 2. And so on. So this is visiting all of the waypoints, and then it will return to the start and dock. Okay, so given all of these nodes and the tutorial files, you should be able to run this fairly easily and perhaps begin extending the domain, extending the sensor interface to be able to be a more complete system and experiment with it. At least that's my hope. After the break, I'm going to go into detail on some more of the less straightforward planning systems, which contain, for example, the long-term autonomy one, which will perform many planning episodes and plan merging in order to construct plans for long horizons. And perhaps give some more insights into how these nodes can be combined in different ways. But that's me for now. It's now time for the coffee break, more or less. Are there any questions before we do?
So in this example, the passive sensor update is updating the waypoint that the robot's at.
Yeah.
It does that before the robot's actually finished with the action. Is there another?
Yeah. So it's using this function. So the AMCL topic is here, and actually AMCL pose, I can just show you what that looks like by going to here, ROS topic pub/AMCL pose. Yeah, there we go. Oh, not pub, sorry, echo. I always do that. Okay, so this is published one message so far. Frame ID map, position this, covariance of this. So it's an estimation of the robot's current position. If I ask it to move, it starts publishing wildly. It's constantly publishing its estimate of the robot's current position. Every time a message is published on this topic, it's passed to the function in that Python file. So this Python file is importing geometry messages pose stamped, which is that message type with the pose and the covariance and the timestamp, the frame ID. That message is being passed into this function, and this function is just checking what's the closest waypoint. So
right.
that's
so
this
what,
part.
what I'm saying is, because
Yeah.
as soon as the closest waypoint is the goal waypoint for that action, that's before the robot actually gets to, it continues moving, it doesn't stop as soon as that's the
Yeah.
closest waypoint. So what's the other condition that it's checking, that the dispatcher's checking for?
Okay.
To say that the action is complete. Because what I expect, if it were just based on this, as soon as the next waypoint or the closest waypoint, the robot would start going to the next waypoint as the point.
That's a good question. So go back to that action interface. Yeah, this is fine. It's not the plan dispatch, in this case, that's deciding when the action's complete. In fact, the action interface is calling MoveBase and waiting for MoveBase to reply action success or action aborted. If MoveBase replies action aborted, then this will reply action failed to the plan execution, and the plan execution will say, okay, the action is finished now and it failed. It's this node's responsibility to decide when the action has finished. And you can, instead of calling this and having this reply when the action is finished, because in this case MoveBase does do that, it actually has its own distance check, and you can set a threshold. I think it's 30 centimeters. You can have this node periodically call the knowledge base query, wait for the action effects to become true, and when they do, say, all right, we're done. Now I can reply action success to the plan execution. If this reports action success in error, that's the state now diverged from what was happening in the real world. The current state is wrong. But if the knowledge base is still correct, the plan execution will still realize the plan has failed. Even though no action has failed, it will say, okay, no, hold on. Our current state has diverged with what was predicted at planning time. The plan is no longer valid, and it will respond with failure. Does that make sense?
So yeah, you can get that. It's basically there are these parallel checks that are happening. Even if, I cross the threshold to get to waypoint 1 or waypoint 0, and the knowledge base gets updated. If the move base fails before I get all the way, the action will still fail.
Yeah.
And then
So in our implementation of the plan execution will return true or false if the plan was successful or not successful. The reasons the plan can fail, there's actually a number of them. One of them is if any action fails, the plan reports failure. The other is if the plan becomes invalid, which is there is an action that needs to be executed, its conditions aren't true, they're supposed to be true, the state's diverged, then it will also report failure. And the responsibility for deciding whether or not an action has passed or failed is not part of the plan execution in this system. Because the plan executor is agnostic to what the actual actions are. We could swap MoveBase for something completely different. I think you were showing that you could replace it with a human.
yes.
Right? And then the fact that the interface has changed means the execution can stay the same. Yeah.
The PetriNet modeler, we had a similar sort of what to do when the transition fails kind of problem. And a PetriNet modeler told me to model the transition as a different state, as an intermediate state. So from waypoint 0 to waypoint 1, there's a new state moving from waypoint 0 to waypoint 1.
Yeah. I don't know if it's.
And then you just wouldn't be in the waypoint 1 state until MoveBase actually puts you there.
So yeah, here is behavior 2.
Yeah.
So this corresponds to one action, but there's actually 3 places. This is the action's ready to start, action starts, the action is ongoing, the action's finished, and now you're here. And these will be, exactly as you said, failure of these behaviors. Whereas in the STRL, these transitions are actually corresponding to the nodes, action start and action end. And these places are the edges, which will be lit or not lit up. Oh well, I actually had the flag on, which made them all multicolored, but generally I'm used to seeing all of the edges as black and red when they're active. So when you have 2 nodes, the action start and the action end, and the edge between them is lit up as red, that means that action is currently executing. But in the planning model, there's no sort of intermediate state. There's just that the action is executing and its invariant must hold. But the position of the robot's not modeled there, you know. Yeah.
So in the later part, are you going to cover the unexpected events?
I'm going to cover strategic tactical planning, which is the way in which we do long-term planning from Pandora. And I'll show you how we build that with the ROSPlan. And then I'll also show a bit of probabilistic planning with RDDL. So it's a completely different plan parsing and plan execution structure, but for that one, it works with non-deterministic models, which is not exactly the same as the unexpected events we spoke about before, in that we're still modeling the probabilities on these actions. I don't have anything prepared for unexpected events, but I'm around all day, so we can, if you're really interested, we can play about. Yeah, just to go back to what you were saying, the process of taking the plan that's correct in your planning model and then converting that into a plan representation which can contain more information, I think is really interesting. And sort of a key part of plan execution is, okay, what do we do with the plan? How do we represent the plan in the first place? It's coffee time. Let's go, come on.